For today's BBISS seminar, we have Fani Boukouvala. She's an associate professor in chemical and biomolecular engineering, and she received her PhD in chemical and biomolecular engineering from Rutgers University, and also studied chemical engineering for her bachelor's in Athens, Greece. So her research focuses on using data analytics and optimization with chemical engineering fundamentals to design complex systems specifically around carbon capture, plastics recycling, and biomanufacturing. Fani was the 2023 Outstanding Young Investigator of the Computing Division of the American Institute of Chemical Engineers and also has an NSF Career Award. And in addition to being a BBISS Fellow, she's also a Fellow within the Energy Equity, Environmental Justice, and Community Engagement Faculty Fellows Program. So her talk today will look at new approaches for chemical conversion of waste plastics to their original raw materials.
Thank you. Okay, so that was a great introduction. I included here, so I'll speak today, but everything I'll talk about today has been highly collaborative. So most of the work I'll talk about today is done by my student Elizabeth Anglu, who is right now, would have been here, but she's taking an exam with Valerie Thomas on life cycle analysis, which actually is something that, you know, her project in the class is something that I'll talk about in this talk. And my student Jacob and the PI, the professor that actually is leading 2 grants that we have on this that led to these results is Karsten Sievers. Other professors involved on various aspects are Chris Jones and Sean Carnair, and their students that are listed here as well. So just very briefly, as you said, my lab, you know, plastics recycling, I just want to show this because plastics recycling is just one of the areas, and I'll focus entirely the talk today on this. But in general, as you mentioned in the introduction, we are chemical engineers who are a little bit do things that are similar to also what industrial engineers do, but you know, we integrate some optimization and a lot of data analysis to design chemical engineering systems with applications in carbon capture, plastics recycling, and some new areas in bioreactor control. So we do a lot of sort of trying to integrate different forms of data to understand chemical engineering systems. And we can start from the very, you know, single process level, but ultimately, as you'll see through the chemical, the case study today, we want to go from the very fundamental chemistry understanding, how it works in a process, how it works, what the actual chemical plant would look like, and maybe how it would impact the supply chain. And so because we're looking at all these different scales, that's where some of the data science stuff we do fit in. But today I won't really talk too much about the methods, but specifically on the application. So, so yes, we were talking about this. There's so much in the news on plastics about the fact that plastic recycling is a myth. And to some extent, the rationale behind this is that, you know, we recycle very little, and there is a history of companies being behind pushing for recycling, maybe knowing that, you know, the technology is not there yet for us to do full closed loop recycling, but perhaps the customer feels good about thinking that, okay, you know, we are recycling, so I can use as much plastic as I want because it's going to be recycled. And that is not the reality right now. So I think part of the, you know, some of these articles have a point in terms of it's not done efficiently right now. And most of the recycling today is done through mechanical recycling, which is partially efficient because every time you sort of heat the plastic and remold it into a new form, it loses some of its properties, so it will have to use virgin raw materials as well. So you know, it's not as efficient as we think. There's also other articles, actually, more recently, because of things that I'll talk about today. Chemical recycling is an alternative to mechanical recycling. You'll find terminologies like advanced recycling also in the literature. And this was a big report that came out recently that generated a lot of discussion. Basically saying that they did a review of all the existing at-scale chemical recycling plants across the US. There's about 11, and they are, not large scale. So if you think about it, their impact actually is not that significant. Chemical recycling, as opposed to mechanical recycling, is it uses chemistry. So it should, with various types of chemistries, and there's different ways you can get there, either convert the plastic to its raw material, so then you can use that raw material again to make plastic without degrading its properties like you would do in mechanical recycling. But how you do it, right? It's the same discussion we had with the direct air capture systems, right? They are chemical plants. They do have waste. They do have emissions. So we should look at the whole impact of these to understand if they're actually helping or not, right? And so the report here essentially claims that based on what we currently have, they're not really doing much. There's hazardous waste that could come from some of these. Some of them operate at very high temperatures and require lots of fuel or a lot of energy to operate. And so there was also a recent story in the news about a company actually had proposed and had moved forward with building one of those facilities and somewhere in Pennsylvania, but there was so much community pushback that actually they ultimately decided not to go forward with it. So there's a lot of things to consider. There's also right now, a lot of our waste, about 80% goes to landfills. There are potential issues with that. In the US, there's been landfills that, because of high temperatures, led to uncontrolled chemical reactions. There's known health risks. And of course, the big issue of us not having enough landfills in the US and moving trash across the globe so that other countries have to deal with our trash, which is, terrible. And there's a lot, actually, of things that also come in the news in terms of big breakthroughs, new research that promises to revolutionize recycling, and then, and then the news that, all chemical recycling is a myth. And so there, you really have to be very, I think, read everything, but hopefully my personal view from being involved in this space is that, yes, we need to design these chemical recycling systems, factoring everything in, but not completely immediately discard everything, because there is some hope. There are some things that are happening in science lately that could lead to sustainable and overall net positive chemical recycling strategies. So,
can I just
yes,
these things talking about breakthroughs, for example, can you give a sense of what breakthroughs are?
Yeah,
kind of the most salient.
So the bottom two are more going into the bio route of taking biomass or animal waste and making materials that have similar properties to, either make materials that have very similar properties to plastics, or actually making chemicals that are precursors to plastics. So, this is completely disrupting the supply chain of, we're no longer using oil and gas, products to make them. The top are, new processes, and the one I'll talk about today is not here in the news, but is what I'll talk about today, are either a new catalyst or a new type of process that for a specific chemical can, with an efficient amount of energy and, not super high temperatures, not a ton of emissions, decompose the polymers, so plastics are polymers, to the monomer that then can be, completely closed loop recycling without waste, without degradation, without the need for virgin plastic, right? So people are playing around with the chemistry, with the catalyst to use, with the design of their processes, and are getting higher conversions, at low temperatures, really.
The bottom ones, does the fact that it's coming from a biosource make it any easier or more difficult at the recycling stage?
No, actually, that's another, well, ultimately, that's what we would want, right? But that's another, you'll find studies that actually say, yes, bioplastics are really good in theory, but right now they cannot be recycled, right?
So they're harder to recycle than?
They're harder to recycle, not because they cannot be recycled, but because the current supply chain doesn't know what to do with them, right? So we have built a supply chain around, the chemical plastics. So now, right now, if there's streams with bioplastics in them, they have to remove them and put them in the landfill, just because they don't currently know, right? So not that that will never happen, but as of now, we've maybe made some progress on bioplastics, but right now they cannot be recycled, right? So
is that always the case? Because you kind of said that either you have new materials that you're making that have similar properties to plastics, or you're creating like precursors. So if you're making like precursors that are,
I think there are some
chemically
examples of, making something that's completely biodegradable, for example, right? That would be different, but
right.
I think there's a gap of those materials may not have reached the point of, having the exact same properties we want. So
right.
There's all these different categories, but yeah.
Okay.
Yeah, if you've made something that's completely biodegradable, then, that's good.
So I'm just curious, so the main issue with like chemical recycling in terms of why people are against it, I think in the previous slide you had like the one that didn't go through in that, in Point Township. Is the main issue just general issues around having new plants, or is there specific chemicals that are used that people are really concerned about?
So there's, I think, there's different chemical recycling routes that have been proposed. Some use highly toxic solvents. But I think from the article, what I got is that there was a general concern that, okay, we're trying to solve one problem, but we might be creating many other problems, and why here, like the same exact discussions that we're having with the reactor capture systems. Yeah.
I'm actually interested in the question I asked from the perspective of, I have a PhD student now who's starting to look at this notion that, companies on the one hand are going, especially in Europe, they're going in the direction of bio-based materials, because these could even be, cradle to gate carbon negative. So from a carbon emissions reduction perspective, that's a strategy. And the EU is increasingly requiring recycled content. And then presumably there's trade-offs, because if the entire economy were to switch to bio-based, then what I'm hearing from you is that at the moment, the recycling portion of it, or achieving the recycling content, would be pretty challenging.
Yeah, or I mean, I'm not sure, actually, I don't know to that extent, like what are the technological challenges to include them in the current recycling streams, right? Is it just pushback because we don't know? but it could be possible easily, or are there like completely new recycling strategies that need to be, I actually don't know that. I remember I did read an article about this on, there's a gap in, we're moving fast with these plastics, but no one has actually looked at the fact that actually none of them are being recycled right now.
Yeah, I'm also curious what the land requirement is. Like, it's almost the same as the biofuel argument.
Yeah.
So.
Yeah, of course, you need to be careful with what is the resource you're planning to use. Yeah, definitely. Okay. So this is all in the news. And so now going a bit into what is happening right now, it's a more linear economy. It's kind of crazy to think that we started mass producing plastics only in the 1950s. And recycling has increased over the years, but it's still at less than 10% of the plastic ever produced has actually been recycled. So there are a lot of efforts, as you said, here in Europe, everywhere, to try to transition to a more global economy. And I think the argument's also that, we should be careful where, who's pushing for what, because obviously we don't want to increase plastic use. One way to do this is to also reduce plastic use, right, altogether. But also, whenever we can, in a sustainable way, figure out ways to actually recycle it and reuse it. So currently, about 80% of US plastic is sent to landfills. In other parts of the supply chain are sorting facilities where different plastics, when they are taken from our bins, are separated and compressed into a bale form. There's pre-processing facilities that shred them into small pieces. And then there's all these different types of recycling approaches. And in the literature, you may find a little bit different. So energy recovery is one. Where unseparated mixed plastic waste is burned to recover energy. That is one thing that we have been doing. Mechanical recycling is where plastics are typically actually, they need to be sorted into the different grades of plastic, and then they are heated, molded into a new product. This is the most widely used thing we do for certain plastics. Then there's chemical recycling, which in literature, you might find both C and D, chemical and feedstock recycling, referred to as chemical recycling, but in my talk, I'll distinguish it. So chemical will talk about anything where using chemistry, the plastic is actually made back into its own raw material that can be used to make the same plastic over and over and over again. Feedstock recycling is when we decompose the plastic into other products, so that you can still use chemistry to make, let's say, oil, like different types of fuel oils from decomposing plastics. So you take a bottle, but then make it into something that someone can use to power their car. And there's a lot of pushback on that, in the sense that we would be taking something but then making something that creates more emissions. But others say, well, then that means we have less dependence on extracting more oil. So there's a lot of things that need to be considered. And then there's the market, where the recovered material goes back to consumers. And sometimes, this recycling process creates different markets if the product is degraded and so on. Okay. This kind of goes through a more visual way of showing sort of that there's a lot of connections, right? So we go from the refinery to make fuels or chemicals. So polymers, plastics come from a refinery. Then they are molded into different products, go to the consumers. they could go into a landfill, mechanically be recycled, but the mechanical recycling route that always needs some combination of the mechanically recycled plastic and virgin plastic to maintain the properties that it needs. And eventually, after certain cycles of mechanical recycling, it will have to go to the landfill because it can no longer be reused. There's chemical recycling. Also, waste plastics can be incinerated to produce electricity, energy. And another very popular, so another technology that's old technology that's actually looked at a lot lately for improvements on your question, like what are some of the breakthroughs? Some of them are actually related to pyrolysis. So this is just a visual representation of where this type of chemical recycling process could come in. But actually, in my talk, I will talk to you about yet another chemical recycling route. So I'll focus more on that. But just to show that, you know, each of these boxes has CO2 emissions. Each of these boxes may have some waste. And so the whole life cycle of this should be considered when we're trying to see, is this actually going to be a good way to handle plastics or not? Okay. So I've already introduced this, mechanical recycling widely used, but every time you do it, you deteriorate some properties and it needs to be mixed with virgin plastic. Chemical recycling here is take the plastic and make it into its raw materials. And a lot of the methods out there, and some of them are the ones that actually have been made into sort of the 11 plants I mentioned in that report I had in that first slide are some of those, and they use toxic solvents or are very energy intensive, and that's how they've gotten a bad reputation. So if we can find better, effective, economic, and safe methods to do this, potentially could have a really good impact. And so this is the focus of my talk, and the project that I've been involved with in the last 4 years is proposing something called mechanochemical depolymerization. And so this is, I have to stress in the next slide, this is not, I didn't have this vision, so my collaborators did. They are the ones driving all the experiments and the chemistry. I'm the one that helps them model things and assess, you know, the impact at scale. So why is this different? It is sort of from the name, you can guess that it has a mechanical piece and a chemical piece. So you're breaking down things and doing chemistry at the same time. This process is done in the systems we call ball mills, which I'll show more. And actually, in a previous BBISS seminar, Dr. Menon was actually also using ball mills for something related to batteries. So they're actually coming back. It's a flexible process, and that does not use as toxic and large amounts of solvents, and it can be done at room temperature. So it doesn't need really high temperatures that could lead to other issues and really high energy requirements. So yes, this is the team, our NSF free project, which is what started us into this. Carsten Sievers is the chemistry and chemical reaction kinetics person that is driving this. And we also have, Carsten Sankar, who is driving the separations piece, Chris Jones, that's the catalysis person, and we have Omar Asensio, who's public policy, and me, who's doing everything I'll talk to you about today. Right, so even though these ball mills exist in many other industries, they can be scaled, and you see here one, I think, from the cement industry. So as a process, operating them in a way where reaction and mechanical breaking is happening at the same time is fairly a new concept. So there's, we need to understand some of the very basic chemistry and physics that is happening at the process level. So what you see here is these ball mills are these large processes that either rotate or shake. They have heavy steel balls in here that, and then you put in your plastic and a catalyst. And as collisions between these solid-solid interactions happen, here are collisions. At the collision, high temperatures are created, but very locally, right? So the whole process can be operated at low temperature, but reaction happens at those collisions. And so the idea is, can we show that with picking the right catalyst for the right plastic, we can completely decompose it into its raw material. But to do that, we need to understand the phenomena. We need to understand the types of collisions and how fast or how much time should the plastic be in the process for it to be converted fully. And so we need models, fundamental models that explain this at that level. And of course, we won't stop there. So really what my lab does in this project is we go from helping model the ball mill process in as much detail as possible, but we don't stop there. So we go from the sort of particle to reactor scale to then, that's just one unit, right? We need to have separations that come after that would separate the product of the reactor into the raw materials that we want. There's recycle streams and lots of things in there. So we then look at the process scale simulation. And then we've also done some work looking at the more larger scale, meaning the supply chain. So we've looked at, okay, well, now that we have an estimate of, what this process would look like, what this process would cost, what scale we can operate it at, what are its environmental impacts, what would happen if we were to take the supply chain of plastics in Georgia and build a plant, that does this versus mechanical recycling, what would the impact on the supply chain be? So starting a little bit at the more fundamental scale, I won't go into details, but this is, we start from lab scale experiments, right? And this is Karsten's really tiny mechanochemical setup where this is a ball mill that shakes. This is a very slowed down video, and it's the simpler one that you can think of. It's just one steel ball in there just for you to see what happens. But you can actually do experiments with many balls in this tiny reactor and different types of feeds. They put, I'm going to focus most of the rest of the talk on one particular plastic, PET, that we've started with. But we are also having ongoing studies with other types of plastics and how they would work in this reactor. And so we go from doing experiments in the lab where we track the balls, and this is the simulation that we develop that can predict the movement of the ball at different conditions, different sizes of balls, different materials of balls that have different weights and so on. And we do a lot of things in the background here, but ultimately what we want is to connect operating conditions of this, right? How fast the balls move to, how many collisions happen, to what yield of depolymerization of PET we can achieve, how much energy is needed, right? Because there needs to be energy that moves this. How much time would the plastic go in there? And we started the experiments with very idealized feeds, so clean PET powder, but we are doing experiments now with actual flakes and chunks of plastic bottles, let's say, that go into there, and they can still be broken down and depolymerized. The simulations get more complicated. We put particles in there and balls and multiple, and we can get things from the simulation like the exact movement of the heavy balls that drive the collisions, that drive the reaction, forces, distribution of energies. And this information all helps us develop a model that we can predict what's going to happen at larger scales.
Something?
Yeah.
What is the scale of these images? When you do this in the lab, I guess that's not the industrial size facility.
No,
because it's very early stage. So
well, yeah. So the idea.
How big are these grinding balls? Is it a tiny thing or is it a big thing? How big should we be?
Yeah. So this one, they're like this.
Pretty small.
Okay. Yeah, pretty small. I can't remember actually, yeah, this is, these are the diameters of the balls.
Millimeters?
Yeah.
So in the neighborhood of 2 centimeters.
Yeah.
My eyes don't look very good.
Yeah. At the same time, you'll see later on, once we have these models, that essentially to train these models, you need material properties of the balls and the polymer, right? And once you've captured the parameters and there's a lot of physics behind these, right? So if we scale it up now, if we put thousands of balls, and we have built a simulation of an industrial scale ball mill with thousands of these balls that are much bigger. Carsten can't build that in his lab, but I can build it in my simulations, right? So that was the original idea. We can get still estimates of the distribution of collisions that happen. And so if that scales, we can say, okay, we need this much residence time at that scale, this much electricity at that scale to get to the conversion that we want. That was the original idea. Yeah. So yes. So, very briefly, we start from the very fundamental scale. But then once we have these conversion models at the process scale, we can now think about what the entire process would look like, right? And we need several other units, as you see here, for separations, right? And this is where Shankar and his students come in, and they have a big lab where they have all these different types of separations: membrane separations, crystallizations, distillation columns. And we did a long study of trying to find the best sequence of post-processing steps after the reactor, right? To get to the product that is the recycled terephthalic acid, TPA, which is the monomer that can be used to make PET again. And we do have, we need to use some water, but this can be recycled. And we do need to use some other chemicals like caustic, which is not that bad, or acetone. And so all of these need to be assessed from a life cycle perspective of, what could be the impact of a process like this at a larger scale, which is what we have done, and I will show you. But ultimately, we have a simulated process that for each of these units, we have validated we can achieve certain separation efficiencies or conversions at the lab scale. And a lot of these processes, apart from the mechanochemical reactor, which was a fairly new type of thing where we needed to focus a lot on understanding the fundamentals, the rest are pretty standard units that as chemical engineers, we establish technology that we have good models for, and we can, go from lab scale predictions to what the process would look like at a large scale in simulation. This is what I was talking about before, right? So once we have a good simulation of the ball mill, this is a much larger ball mill. So we base this on the, let's say, how much PET is used and could be recycled in the state of Georgia. So that comes to about 2,000 kilograms per hour. And so we looked at, okay, what would the size of the reactor have to be? How many balls would we need to put in to reach the fill level, and the number of collisions that we saw at the lab scale that could get us to a really good conversion. And I forgot to mention a really important thing, that for PET, we are seeing, close to 100% conversion of the plastic to the raw material, even when they put in, cut up pieces of plastic bottles.
So that's in your actual
Reactor.
small one in the lab?
Yes, yeah.
What, is there any factoring in of any kind of contamination?
Yes, good, very good question. So we have looked at dyes, various dyes, and actually some money came from a company, a textile company, because PET actually also is used a lot in clothes, and we have also looked at putting textile waste into it, and so some of the separations that you see, so in some ways this is kind of an over-designed system to also separate out some dyes and small particles or things like that that could come from some contaminated sources. Of course, not, real. Let's say we took a stream that's mixed plastics, right? That that we haven't looked at. We're looking at major source of PET with some minor impurities for now. But yeah, that is a really good question. Yeah.
What are the catalysts?
So I have the reactions here. So essentially the reaction that's happening here is PET and caustic produces ethylene glycol and Na2PA that is then converted to TPA.
So just acids or bases?
Yes.
Okay.
Yeah. Okay, and you can see that whenever you ask me a chemistry question, I freak out.
It's okay, I'm a failed chemical engineer. That led to being a chemist. I'm also having panic attacks every time you show those flow charts and balanced equations. No, don't show that again. Don't do it.
Okay. Okay, I'll go a little faster. But yeah, with this process flow sheet, what can we do? We can estimate at this scale of, let's say, processing all the PET produced in Georgia, the operating expenses, how much raw materials, utilities, and so on are going to cost, and the capital investment. And so as chemical engineers, we start with cost, but we don't stop there. And we see that, for example, the utilities are low. Actually, the majority of the operating cost comes from the raw materials, which is something we expected because this process is not operated at very high temperatures.
Which raw materials? The steel balls or the?
No, it's the PET. Yeah.
Okay.
The PET and the caustic and those. Yeah.
Right.
Compared.
But it will be waste.
Yes, and so this is why we do analyses of, okay, so this is if we were to build this plant, the cash flow over, assuming we'll build it in 2025 over to 2039, we can become profitable after 3 years, assuming some specific prices. And this goes to your question of, what is the cost of PET bale right now? What could, we do sensitivity analysis to see if there's different policies that will affect, the waste price of PET. Of course, the process can become more profitable, but based on the current costs of if we were actually, we started with ideal PET flakes, but approximate cost of PET waste is here. So actually, it could be even more profitable if there's subsidies or things like that, would make using waste PET more profitable. Generally, by doing the sensitivity analysis, we confirmed again that, we looked at other aspects like, replacing certain units like the membrane life cycle, changing some temperatures in some units, or replacing the steel balls, as you said, because after some years they will have some degradation and so on. But these are very small costs compared to what would happen if the feedstock prices actually change. So the feedstock is actually what's really driving the economics here. And we compared it, so there's, similar to us, there's other types of chemical recycling strategies being proposed, like enzymatic hydrolysis, where we use enzymes, more of a bio process, methanolysis, where methanol is used to do the depolymerization. And there's literature out there, coming up with this sort of cost per kilogram of this technology. So where do we stand in terms of that? And also production of virgin PET from, the traditional route. And so we do okay in terms of cost, right? Which is important. But yes, this is something that my student has been working on as part of Valerie Thomas's class that she's taking this semester, and in collaboration with Patricia on now looking at the life cycle of this process, right? So the boundary here is, we're assuming the waste is coming in, we're doing our mechanochemical recycling, and then we're also making plastic again, right? We need to factor in the fact that, we made this product, now we need to make it into plastic again. So factoring the emissions, the waste, the resources around this entire boundary, okay? And so in doing so, and I am new to this, and so some of the things here I don't know all the details, but Valerie really helped Elizabeth do this, and I am very grateful. So you look at all your inputs, electricity, steam, materials, all the different chemicals, water, and so on, potential traces of waste that we have, assuming that we've done everything we can in our system to recycle everything, but always in these systems there could be, tiny, small, particles that may escape in some waste stream. So we are trying to factor everything here. And there are resources, databases where you can look at greenhouse gas emissions, CO2 equivalent emissions for all of these different inputs and outputs. And so using these models, we can get a CO2 equivalent for this entire integrated process, factoring also the remaking of the plastic, right? The entire closed loop process. And that comes out to be 3.98 kilograms of CO2 equivalent per kilogram of PET made, okay? Now, this does not account for what in life cycle analysis is credit or allocation of byproducts, right? So through this process, we're making some products that we can then sell, or they can replace or displace the current production of this. And so these are ethylene glycol and sodium sulfate. And so there's different ways through life cycle analysis to account for your adjusted CO2, GHG emissions, CO2 equivalent per kilogram of PET by subtracting or factoring, the effect that you would have by also producing these co-products. And there's different techniques that I don't fully yet understand that could lead to very different results. But from now on, we will use the more conservative one, which is now we went from 3.98 to 2.67 kilogram CO2 equivalent. So how does that compare to virgin PET production? So, right, if we did all of this and we emitted more CO2, then that's terrible, right? So we are not there. And how does it compare to mechanical recycling? It is higher than mechanical recycling, obviously, because mechanical recycling doesn't have all those units. So this is something that needs to be factored in. However, when we go to the supply chain level, where you start to look at the more long-term effects of doing mechanical recycling, even if the impacts here are smaller in number, because you will keep on using more virgin PET, ultimately it actually becomes worse. And how does it compare to other proposed chemical recycling technologies? Based on the assumptions, and everything is at a very low early stage, and it seems to be doing well. It seems to be promising, but of course we need to keep refining these estimates. And the other thing that you can do with tools that are out there, like the recipe tool, that is another thing that Elizabeth learned from Valerie's class, is look at more long-term impacts. So midpoint impacts on human health, soil, fresh water, marine ecosystems, accounting for things that could be waste from your process and could be very long-term, have long-term impacts to health and the natural ecosystem. And it seems like the numbers are low. And of course, we need to look at these numbers in the context of also, the alternatives of landfilling or, virgin production and so on. So it seems like, based on everything we have assumed so far, it's doing pretty well. And so far, these are very preliminary numbers. And as we keep learning more about the process, at least now we have the tools to plug in new numbers and see how the impacts could be affected. So I'll wrap up with, now how we go to the more larger scale, which is the supply chain. So we started with looking at, obviously, because we're assuming we're going to get PET, right? But right now, how much PET is being recycled? How much clean PET? What happens? How is it sorted? How much is there? And so we had this question of, okay, what is the current supply chain of plastics? You saw one of the earlier headlines I had on the news slide that, you think there's a study where people put tracking devices in plastic bags they threw in recycling bins at Walmart, and they ended up in Malaysia. There's things, so understanding the availability, the demand, the supply, and how potentially a new chemical recycling strategy could affect that is important. So we started collecting data, and we said, let's first focus on the state of Georgia. Of course, that might be inadequate because there could be movement across states, across state boundaries. So, but for now, in trying to understand sort of what happens, at least locally, we collected data that exists from the state of Georgia and EPA in terms of amounts recycled, amounts produced or consumed, and the two most data-heavy plastics were PET and HDPE, high density polyethylene. So even though we're not really actually studying recycling routes for HDPE for now, we included it in this analysis. And so we have data on where all the transfer stations, where all the landfills, where all the current mechanical recycling facilities, so all these PET recycling nodes are mechanical recycling, and where are some potential markets. These are actually also documented, like companies that could actually take mechanically recycled PET and reuse it or make something else out of it. And we formulated a mathematical model that sort of looks at economic and environmental objectives of, well, if we want to recycle, if we want to make sure there's some information on demands of these markets and availability. And so if we wanted to look at minimizing a cost of a supply chain or actually minimizing the greenhouse gas emissions of a supply chain, factoring in transportation as across nodes, right? What would that look like? Under different objectives, would the supply chain change, and what is the impact of transportation, and so on? And also, if we are to embed now chemical recycling facilities in these, what would the impact be? Are we better off or are we worse? So that's, the model looks like this. But a bunch of constraints, mass balances of different different plastics, and meeting some demands and capacities of the different nodes and so on. And this is all information that we're able to find. That's not the model equations are not that important, but what's important in the results is that we looked at different landfill scenarios, right? So right now, 80% goes to the landfill, so that's what we call business as usual scenario. But we see, especially in Europe, policies that are banning landfills altogether. So, and some states in the US, I believe. So we're looking at what if the scenario of how much we can send to the landfill changes. What is the supply chain problem is solved, and now we're looking at, let's say, all plastics being moved to mechanical or chemical recycling facilities. What is the transportation impact on emissions? What is the PET and HDPE operations on emissions? And so we see that actually with less landfill, we have less emissions, and which is counterintuitive because landfill is associating with very low emissions. But it is, what's driving it is the new virgin PET that will keep needing to be replaced, that has very high emissions. So there is a case for incorporating closed loop chemical recycling. And you see here in the effects of, when we go from 0 to 90% landfill, the impact of how much new virgin PET we need. And you also see that between PET and HDPE, there's different conclusions. And that has to do with the fact that current strategies, current costs and emissions of technologies for chemically recycling HDPE versus PET are very different. So perhaps there are solutions for a specific type of plastics that won't hold for other types of plastics that we need to consider.
Is this why you're looking at PET first?
Actually, no, the decision was mostly because it is, in fact, the easiest to depolymerize. Oh. Which, of course, translates to the fact that, the numbers actually are pretty good, right?
Sorry, but this graph is assuming mechanical, like the current condition.
It's assuming that we can actually pick, right? The model is picking at the different nodes whether it should do mechanical or chemical recycling under different landfill scenarios. We also see something we didn't expect, that or, you know, we were curious that transportation actually is not as significant in terms of both cost and emissions when it comes to this problem.
Can I ask a question?
Yeah.
When you say landfill scenario,
Mhm.
so that means you're not optimizing your fixing.
Yes, so we can leave everything free, but yeah, that would be a more difficult problem. We're treating the amount that goes to landfill as a fixed decision, as if it's a policy decision, for example, right? And then based on that.
And you assume that is proportional, like every source of PET would be 40% sent to landfill and 60% be available for recycling? Or do you optimize across the entire network to get the 40% landfill?
Yeah, we optimize across the entire network, right? Assuming that each of our landfill nodes has a certain capacity. In all, we can landfill, you know, 80% of what we produce or 70% of what we produce. Now, where it goes, it's up
But
to.
you're imposing the 80%.
Yes,
landfill.
yeah,
I see.
yeah. And that's mostly driven by.
Why do it that way as opposed to just optimize?
So one reason is because the current scenario is that about 80% goes to landfill. So we wanted to see if we start slowly reducing, you know, the amount of landfilling or what the impact would be.
And the reason 80% goes to landfill right now is it lack of capacity or is it leakage at different stages of the system, or is it transportation cost?
It's lack of it's lack of capacity. It's also that strategies to create clean PET, you know, the sorting and also how much we recycle, right? So this is assuming that, you know, the 10% is the good citizens that, you know, recycle and clean. The rest, you know, don't recycle, so it goes straight to the landfill. So it's all of those things factoring in, right? So 80% of what is actually consumed ends up in a landfill, either because of not being sorted properly or not being recycled to begin with.
Yeah. So then the more realistic scenarios here are still probably at the 80%.
Yes.
Landfill.
Well,
it's not like the introduction of this new mechanical recycling system would fix any of those issues, right?
Yeah, no. And that's why we have Omar on the team from public policy to see, you know, if you develop a new technology like that, what could be some consumer incentives or consumer behavior type things we could try to do to see if someone knew that actually now there's a technology that would take PET and you know, closed loop recycle it, and it's actually not being burnt or used to make new transportation oil, you know, would they be likely to recycle more, right? So, but yeah, that all changing mass behavior is something that's way outside my chemical engineering background.
Right.
But yeah, we are out of time. So ultimately, there are trade-offs between economic and environmentally friendly scenarios. So you can do what we call multi-objective optimization, where you're looking at, well, if you're trying to combine, and for the PET and the HDPE, there are different proposed strategies. For example, for HDPE, yet mechanical recycling is actually preferred because technology, based on the metrics right now, is not good enough to make it as environmentally friendly or economic. But for PET, actually, the current chemical recycling data shows that actually there's a lot of promise. But again, here, preliminary, and at least this tool gives us the ability to now test different scenarios, right? So my conclusions is that I think, there is hope, and we shouldn't, based on bad experience with chemical recycling in the past, sort of abandon all hope. But of course, in designing these, they are, new chemical plants. We should be very careful with looking at all the aspects, and we really need to study them further to look at good questions that you guys have asked me today about impurities, mixed feed streams, waste streams, community impact, and thorough life cycle analysis and cumulative impacts. And of course, always advocating for, if we can, reducing the use of plastics altogether. And in general, I wanted to just conclude that, through my involvement with you, BBISS, and SCORE, a lot of things that came here are, and the way I think about this problem are, I'm heavily influenced from this, and I really, really appreciate it. And I think we should really have mandatory courses for chemical engineering students on life cycle and social impacts and community impacts, and this is something I will keep advocating for. I had something on the bio work we're doing, but I don't want to go into that. And yeah, I really want to acknowledge, of course, the technical team, the NSF-EFRI team, but also SCORE, BBISS, and RBI, who has given us some seed funding to do the bio processing work.
Thank you.